Hello and welcome back to another episode of Math with Son. Today, we're going to be doing some systems of equations specifically by graphing. And where we need to start with that is what type of scenarios you can get with systems of equations of lines. Okay, so there are really only three options. You can have one solution, infinitely many solutions, or no solutions provided they're lines. If you have like a parabola or something, that's a little different. Now, one solution would look like one line doing its very own thing, and then another line that happens to go through it, and they just intersect at a given point. So this specific point, that intersection, that is the one solution that it would have. And if that happens, if you get a solution at all, you have a consistent system of equations. And because both of these lines, this purple one and this black one, are doing their own thing, then it is independent lines. Okay? Now, if it's infinitely many solutions, that means that one line is here, and then the other line is directly on top of it, which I did squiggly just so you could kind of see that there are two lines directly on top of each other. And if that is the case, then it is still consistent because we are still getting a solution. The problem is that they're infinitely many solutions because it's one line on top of another, and that means that these two lines are dependent on each other. And then the last scenario that you get is no solution. No solution graphs could be any given slope, and the difference is that both of the lines are parallel to each other and never intersect. If they don't intersect at all, then they have no solutions, and if that is the case, then we are getting an inconsistent system of equations. Okay? So we got three examples for you and then some variants to that. So in this case, we have y equals 2x minus 7 and 2y plus x is equal to 6. I'm going to start with the equation that's a little easier, which is 2x minus 7. We got to go down by 7. 1, 2, 3, 4, 5, 6, 7 for the y-intercept. And then the slope is 2 over 1. You can always put a 1 underneath. So from here, we got to go up by 2 over by 1, up by 2 over by 1, up by 2 over by 1, up by 2 over by 1. Notice how I did a lot of up by 2s and over by 1s. That is recommended that you do not just use 2 points, because if you use 2 points, there's a chance that you make your line a little less accurate, and therefore you don't get the correct solution because you're looking for where these two things intersect. Now the other equation's 2y plus x is equal to 6. You can solve this with the x-intercepts and the y-intercepts, or you could solve for y. If you solve for the x-intercept, you would cover up the y, you'd get x is equal to 6, and then the y-intercept, y would equal 3. But for practice, I'm going to get it in y equals mx plus b format. We're going to subtract that x over, you get negative x plus 6. Divide everything by 2, you get y is equal to negative 1/2 x plus 3. Divide everything individually by 2. So it has the y-intercept of 3, 1, 2, 3. And now it's going down 1 over by 2, down 1 over by 2, down 1 over by 2. Not that it's needed because we have that intersection point, that solution. Not only that, but if we did graph it with the intersections, you would be able to hopefully find the correct intersection as well. The slope method works a little bit better because you get a few more points rather than just 2 with the 2 intercepts, the x and y. So we got that one solution. It is at 1, 2, 3, 4, up by 1, so 4, 1. And because it has one solution, it is consistently getting a solution, and they are independent lines. Okay. The next two equations we have are very similar. They're all in point-slope form because tends to be a harder format. Remember, with point-slope form, you don't need to distribute. In fact, if you did, it would be kind of nasty to have to distribute and figure out what 2/3 of 1 is. But that doesn't mean you can't get your point by changing the sign of the 1 to make that a -1 and changing the sign of the 3, -3, to make that a +3. So I'm going to plot the point at -1 +3. And that is left by 1, up by 1, 2, 3. And it has a slope of 2/3. So I'm going to go up by 2, over by 1, 2, 3. And in the other direction, I'm going to go the opposite direction, down by 2, and to the left by 1, 2, 3, to kind of continue that line. And by doing that, I ensure that I have at least got a little bit of a straighter line. Hopefully my solution's not beyond those 3 points. Now the other point, we have to change the sign for -4 for that other line and change the sign +1 for that other line. So we got to plot the point at 1, 2, 3, -4, +1, which you may notice is exact same dot, which you might be thinking, oh, there's my solution, -4, +1. But what happens if I do the slope 2/3? I go up by 2 and over by 3, and up by 2 and over by 3. I have the exact same line here. They're one line on top of the other, which means that this is infinite solutions. And if it's infinite solutions, then this would mean that they are consistent and dependent. Which I think I spelled dependent wrong. I got a few too many D's in there. So, third and final one on this sheet, we have the exact same line, y minus 3, 2/3, x plus 1. So why bother redoing everything? But it is going to have the point at -1, -3, +3, change the sign for both. -1, +3, and then I go up by 2, over by 3. Other direction by 2, other direction by 3. I can graph it with a straight edge because that makes things a little more precise. And then the other point for the other line, we have to change the sign. I get +2 and -5. So +2, right by 2, down by 1, 2, 3, 4, 5. If my slope is 2 over 3 again, and other direction 2 over by 3, these two things are parallel. They are never going to intersect each other. And if they never intersect each other, that means that they are inconsistent and they have no solution. Okay? So another takeaway here is if anything has the exact same slope, they're either going to be no solution or infinite solution. So pay attention to that. If you recognize that something has the exact same slope, then it's got to be either no solution or infinite solution. You're just narrowing it down. All right, we got some variations and some limitations with graphing. So this first one, for both of these variations, I've graphed one line for you, which sometimes throws people off. So this first line graph for you is 3x minus 2. And then we want to find the solutions using for the system with the other equation being 2x minus 5. So we have -5 for the other equation for the y-intercept, and we go up by 2 and over by 1, and up by 2 and over by 1, up by 2 and over by 1. It looks like this one is getting a little bit further away over here, so maybe have to go the other direction, down by 2, over by 1, down by 2, over by 1, down by 2, over by 1. And you realize that this is not fun. That's a lot of points. And it's kind of hard to tell, where is this intersection point? What is that point right there? All right. So if we know we were at -5 and we went down by 2, I'm at -7 over by 1. So I'm at -7 here. And then if I went down by 2 again and over by 1, I'm at -9. Have I reached the intersection? Not quite. If I go down by 2 and over by 1 again, I'd be at -11, and I'm definitely to the left by 1, 2, 3. So I have a solution point at -3, -11. It is a little bit of a mystery, but I'm pretty confident with that. Now, there is a limitation here. The limitation is what happens if it's way, way off the graph? You know, what if I had two solutions and it was like way over here, you know? Like, what do we do? What do we do then? So there has to be potentially a different method beyond graphing as well, all right, which we will get into in the next lesson. The next equation that we have is graphed for us, y equals -2/3 x plus 4, got it, and we're graphing y equals 2x plus 1, so it has a y-intercept of 1, and we are going up by 2 and over by 1. And if we look at this graph, and if I were to zoom in, really fine-tune zoom in here, we would realize that this point right here looks like it's at 1, 3-ish. 1, 3 and a little bit, point something. And we're not going to be able to tell just by looking at it what it actually is. So what could we do there? Well, with graphing, you are out of luck. Unless you have a graphing calculator, it cannot tell you the solution just by looking at it. You have to be able to have a different method, okay? And in reality, this solution was 1.125, comma 3.25. You would not get that by just glancing and be like, well, it looks like it's about a quarter and apparently an eighth. You're not going to get that. So there has to be another method, and that is eliminate the limitations to the graphing method. Okay, so some notes and summary. Graphing is good for determining the three kind of solutions. Kind of solutions being one solution, it is good for infinite solution, and it is good for no solution. And then we could further classify it as independent and consistent and things like that. But it is not good for decimals. Not good for decimals. Okay? And as a reminder, infinite and no solution, the slopes are the same. Okay, so if it's not good for decimals, we must have two other methods that we're about to learn, the substitution method in the next video and the elimination method in the next video. Okay, so I would recommend stay tuned for that as a little teaser. But until then, stay positive, my friends, and I will see y'all later. Bye.